So a couple things off the top. We go to Canvas. I put up, where is it? Final exam materials. Kind of, oh, sorry. So we have these practice exams here. We'll start going through practice exam B today. Oh, you guys can't see it in class. There we go. So we'll be going through practice exam B today, unless there's specific questions on practice exam A. I did put up on our YouTube playlist kind of 3 different videos. So I think I broke it down into questions 1 through 3, 4 through 6, and then 7 through 10. I also added some additional questions that I thought might be good, wink, wink, to know for the exam. So kind of that last one has some additional questions that weren't on the practice exam that I potentially could ask you, okay? So those would be helpful as you're working through that at practice exam A. Also, where is it? Assignments. So just like with the iClickers, I kind of created this Learn Smart with your lowest Learn Smart drop, so you can kind of see what your final Learn Smart grade would be there. And once again, I'll do a similar thing for the Connect and the Excel once these last 2 assignments are kind of due, or due date has passed, right, after Monday. I've also graded the 4th Excel, so you can kind of see if you submitted that, what your grade was there. And that should kind of do it in terms of kind of where we're at with things. Are there any questions for me kind of moving forward before we kind of jump into this exam review? Okay. So we've got practice exam B here. We can kind of go through some of the older stuff. I'll probably jump around a little bit just so that we see some old stuff, and then kind of also have some linear regression examples here today. So we'll go back and kind of look at this example where suppose we want to know, we've got 2 different time periods, 2010, 2016. We've got 30 CEOs and 25 CEOs from those 2 time periods, and we find a sample kind of mean for the average age in those time periods of CEOs of 45 and 50. We also kind of have these associated sample variances, right? So we've only got sample variances. So to kind of keep things, kind of track of things, I think a good thing to do would be to run through this before we even tackle this question. This will just help more generally as we get closer to the final. So anytime we've got, right, we're just looking at stuff since the last exam. So anytime we're like comparing 2 sample means and we actually have known population variances, this is going to be where we can use that standard normal distribution. If we're looking at the difference in sample proportions, we get to use that standard normal distribution. Okay. So moving from there, if we have examples where we're looking at the difference in sample means, but we only have sample variances, this is where we're going to use that student T. Some other examples where we use the student T, if we're looking at that mean difference, because there all we had was a sample variance of that difference variable. And then finally, we can actually look at or think about doing hypothesis testing with our coefficients, and they had kind of their associated standard error. So these are going to be the 3 scenarios where we can use, or we should be using, that student T distribution. Okay. Any questions on that? So it might be a good thing to kind of have written down as you're kind of working through problems. Anytime you see proportions or you know the population variances, that's the only time you use that standard normal. When you have sample variances, the difference in sample means, or the mean difference, you only have a sample variance. And then of course for our coefficients, we always use that student T distribution. Okay. Yeah.
So for the Excel ones, could you go over very quickly which ones you're supposed to use?
See if I can remember this off the top of my head. So part 1, you would have been looking at proportions. So this is where you had 2 different time periods and we were looking at like the proportion of enrollment being over 10,000, I think. So that should have been that standard normal distribution. Problem 2, you had male and female enrollment, but you weren't given a population variance. So all you had was sample variances. So you should have been using the student T. And then on problem 3, for that mean difference, all you have is a sample variance. You should have been looking at that difference between, what was it, October 2021 and October 2020. I'll get an answer key up for that 4th Excel as well. I have it ready to go. So I'll get that posted after my classes here this afternoon. But yeah, that would have been the order of that Excel summary. Yep. Any other questions? We're gonna go back to the so that problem, all we had were sample variances. You'll kind of notice fairly friendly and kind of even use that notation as well. Okay. So if you see that sample variance notation, if you were to look at your formula sheet, we've got confidence intervals and test statistics. And it kind of reminds you when you're looking for the difference in sample means and all you have are these sample variances, you need to be using that student T. Right? So that formula sheet even kind of helps remind you of that. So I want to do a 95% confidence interval. So I've got my 3 confidence intervals. I just said I'm going to use the one where I'm looking at the difference in sample means and I only have sample variances. So, oops, there we go. So what we're going to be thinking about here is we're just going to be plugging our values in, right? So let's see if I can remember these correctly. I believe, like most cases, you want to take the newest time period minus the old. So I believe the first average age was, or the average age in the newer time period was 50, minus the older time period, we're kind of group 2 there, which the average age was 45. We'll then add to get our upper bound, subtract to get our lower bound. We're going to be looking up here a t value that gives us alpha over the 2 in the tail. I believe it was the 95% confidence interval. So alpha would be 0.05 divided by 2, so 0.025. We'd have to be given an assumed true degrees of freedom here, because when we had sample means and all we had were sample variances, we had that real nasty degrees of freedom equation that I even put in there for you on that Excel assignment. So we'll look back in a second. I'm sure I gave you an assumed true degrees of freedom here. And then we multiply that by the square root of each group's sample variance over its sample size. So this is where I'm going to have to go back because I can't remember these values. So what? 25 over 25. That one's easy enough. Plus 36 over 50. Now the only thing left to do is look up that t value, right? And we had this assumed true degrees of freedom of 46, right? That was given to us, okay? And I would give that to you on the exam as well. So here's our t table. We'll zoom in here. We wanted 0.025 on each side of my confidence interval. So we're going to use this column. We're then going to go down to degrees of freedom of 46. So 2.013. Right? And now it's just a matter of getting this entered into our calculator. Okay. So once we kind of look that t value up, we plug that in, we're done. Okay. Any questions over kind of the process of that? Oh, this will be practice exam B. Oh, really? Final exam B. All right, let me look it up here. Oops. We should have said something earlier. I might have grabbed the wrong one. So let's look. Files, final exam materials, practice exam B. Let's download it here. Might get mad because I already have a. Oh, well. So you guys have a different one. All right, that's fine. I'm going to finish this one and kind of show you a little bit with this. We'll then kind of return to the one you have. So I must have put up another set of questions I had for the final practice exams. So we'll finish out this one, and then I'll kind of go back to the actual one. But I do think it's useful. I wrote the exam, so I know that maybe this one's a little bit good one to go over. So really from there, it's just a matter of kind of doing that computation. You know, I guess if we're doing this here, I could do this in Excel for us so we can identify the correct answer here. But once you have the setup, it should just be a matter of getting it entered into our calculator. So here, I'm just going to type out, oops. Use Excel to be a calculator here. So I think it was what, 50 minus 45. We'll find the lower bound here, 2.013 times square root of 25 over 25 plus 36 over 50. So 2.34-ish. So I think I probably rounded kind of a little bit. So about 2.2. I'm getting, that doesn't look right. Give me 1 second. Did I enter something in here? 36 over 50, 25 over 25, 2.013. So about 2.3. Well, I guess that's good. Maybe this is why I didn't put this practice exam up, but that's kind of the process through which you would do. I think it's good to kind of get some practice looking up these student t-distributions, because like I said, I know that I'll ask you that kind of on the exam, right? All right, so now we'll go back and use the correct practice exam. So thanks for saying something. So this is a similar example, right? In terms of we're looking for a confidence interval. However, now we've got two sample proportions. Right? So if I'm dealing with proportions, what distribution should I be using? I just said always can use that Z or that standard normal. We go to that formula sheet. We've got our confidence intervals. Now we're going to be using the one for sample proportions, right? So once again, it's just going to be a matter of plugging all these values in. We were given the sample proportions for the two groups. We have our sample sizes. So it's going to look very similar, right? It's just now I've got what? Group one is 0.32. So it's gun ownership in the US minus the gun ownership in Canada, right? So my confidence interval should be centered around what? 0.06. That was kind of like the sample difference that I found here. Okay. So if I'm looking at these, if they didn't include 0.06, I could rule them out. Well, actually, it looks like these two only have negative values, right? So I actually could rule these ones out right away. I know it's going to be either A or B. From there, it's just a matter of plugging in what I know. So 0.32 times 1 minus 0.32 divided by the sample size. So that was what? This one is kind of easy. It's 250 for each group. And then plus 0.26, I'm running out of room, times 1 minus 0.26 over 250 there. So once I get that, the only thing left that I need to find was that Z value that gave me alpha over 2 in the tail. So I believe it asked for the 90% confidence interval. So alpha is going to be 0.1. 0.1 over 2 is 0.05. Now I could use the Z table here, or I can use a little shortcut, which is I want 0.05 in that each side of my confidence interval. I can use that last row of my student T table because it gives me the standard normal values. So it looks like here 1.645. Okay. So now I just plug in that 1.645, and that should give me my upper and lower bound, right? Add that margin of error to get my upper bound, subtract that margin of error to get my lower bound. Okay. Any questions on that? I forgot that calculator, so I can keep using Excel here. So, oops, I need to go to share screen here. And I'll leave this up as I can do this real quick. Unless anybody beats me to it, if anybody calculates it, let me know what it ends up being. Otherwise, I'll kind of use my Excel calculator here. So what? 0.06 minus 1.645 times the square root of 0.32 times 1 minus 0.32 divided by 250 plus 0.26 times 1 minus 0.26 divided by 250. Right? So negative 0.007 approximately. So I go back here, negative 0.007. I don't even have to really calculate the upper bound here. Just calculating one of them allows me to identify the correct answer. Okay. I could go through and add that margin of error and reproduce that 0.127 if I had some extra time and just really wanted to, feel comfortable or confident with it. But once I, notice once I calculate one of the upper or lower bounds, I'll be okay here. Now, one thing to make sure on these is really be careful that you're taking the correct group as group one and subtracting in the right order. I saw a lot of that on the Excel assignment, people kind of flipping the groups so that you basically end up with the same answer, but it'll be like negative instead of positive or vice versa. So here, look at the note kind of, if we're looking at this notation, and actually here, let's make sure we do right, group one minus group two, right? So US minus Canada, and then kind of work that one out. Okay. Now, what if I wanted to do the hypothesis test with this, and I wanted to come up with a test statistic? So I give you the hypothesis test here, which let's just try to interpret. If I have what I'm trying to test for is that difference is greater than 0. So the way we set this up, we took US minus Canada. So if I'm wanting to test for whether or not that difference is greater than 0, what I'm really trying to test for is whether or not the US has a higher proportion of gun ownership than Canada. Right? But that was given to me. The hypothesis test was given to me in this problem. So I've got what type of tailed test here? So I look at my alternative hypothesis. I've got a right-tailed or a greater than test. Okay. So to find that test, and that doesn't necessarily matter for finding the test statistic, but trying to paint the kind of big picture here. So what I'm going to do is look at what sample difference I found. We already said that was 0.06. So if I look at my formula sheet, here's my 3 test statistical equations. Here's the one that I need to use for proportions, right? This is where we kind of had this intermediate P bar we had to calculate. So really, when it comes to these test statistical equations, it's just a matter of I identify the correct equation. I don't even have to look anything up here. I plug in 0.32, 0.26, everywhere where I've got my sample portions. My sample sizes were all 250, so that one I can't mix anything up here, so that's nice. And it's just a matter of kind of going through that process. So I'm not going to necessarily write all this down and kind of, I think the test statistic one should hopefully be some of the easier points in the terms of once you get the process down of I was given the notation, I've got sample proportion differences. Here's my 3 test statistical equations. I just use the one that has proportions in it. Right? Now, one thing just to kind of point out here is even without doing the calculation, I might be able to rule out certain answers. So we think about what we're doing is we've got this distribution for that difference in sample proportions, which should be centered around the true difference. However, we've got kind of an assumed true difference of 0. The sample difference we found was what? 0.32 minus 0.26, so 0.06. That's going to translate to a test statistic that, because we're dealing with proportion, comes from the standard normal distribution. So remember that test statistic, or Z statistic here, represents the number of standard deviations away the sample evidence we found was from the assumed true difference. So if it's to the right of that assumed true difference, it's going to be a positive test statistic. And that kind of makes sense for a right-tailed test. The only evidence here that would go against the null would be evidence that, that difference is above 0. That's the only thing that would go against the null here and support the alternative. So we found evidence that goes against the null, but does it go against it enough, right? So we plug everything in, calculate that test statistic. We know it's going to be positive, so we could rule out B right away. A looks really fishy to me. It's very high, 36 standard deviations away. I theoretically can't rule that out, but likelihood-wise, that's probably not going to be the answer. So it's probably between C and D. If I had to go out on a limb, I don't know if anyone else calculated it as we're working through this. My guess is it's going to be D, because what does C look like? Instead of a value for the test statistic, 1.96 often is the value for critical value, right? Kind of associated with having what, 0.025 in the tail. So it could be 1.96, but my guess is it's not. I'm guessing I put that up there as kind of a, maybe we could kind of, if we work through enough problems, we can kind of recognize these benchmark values. So I think if you plug everything in, you should get that test statistic of 1.47. Like I said, I can walk through and I can write all that out, but I think that our time's probably better used working through some more of these problems. Okay? Any questions on that before we keep moving? Since I didn't completely work through kind of plugging all those values in. Okay. So if you got that one wrong, it's going to be a problem if I then ask you to find the test statistic, or it's not test statistic, p-value from that test statistic. So here, instead, I give you an assumed true test statistic. Right? Now, this one happens to be close to what the true test statistic is. That is often not the case. Sometimes I even change the sign because I'm trying to get at different principles. So let's assume instead of 1.47, we found 1.67. And we've got a right-tailed test. So if we want to find the p-value, remember the p-value represents the probability we saw the test statistic we did, or anything more extreme that goes against the null. Well, for a right-tailed test, that's anything to the right-hand side. So this represents our p-value. How can I find that? Well, I can use my standard normal table. It'll tell me the area to the left of 1.67. I wanted the area to the right, so then I would have to subtract it from 1. I noticed, some issues with kind of p-values on the Excel. One thing I would say is drawing this out often helps, right? Drawing out your right-tailed, left-tailed, or two-tailed tests often helps with kind of the process of then finding what that p-value is. And I'll blow this up here in just a second. So I'm going to look up on my standard normal table this value of 1.67. So I scroll down here, 1.67, so 0.9525. So 0.9525. I wanted the area to the right, so I subtract that from 1. So what? 0.0475. Okay. So that's my p-value. And I think it asks about rejection decisions. So I'm not sure that the whole problem even if it didn't, I could ask you about the rejection decision here. So once I have that p-value, I only reject the null if my p-value is less than alpha. I believe the alpha in this problem was told to us to be 0.05. My p-value is 0.0475. So here, at the 5% significance level, or with 95% confidence, I could reject that assumed true difference of 0, right? Or less than, I think it was less than or equal to 0. Right? Any questions on that one? All right, so we got our p-value and our rejection decision. So that would be 0.0475, and we reject it. So I'll point out a couple things here. One, what would change if I instead asked for a two-tailed test? What's the only additional step I would have here? If I had a two-tailed test, it would have been equally as likely for me to see something that went against the null, but on the other side, right? Because now evidence on the left side would go against that assumed true difference of being exactly equal to 0. So all I would do is kind of multiply this by 2, and I get what? 0.094, no, 0.095, right? So that's the only thing that would change for a two-tailed test. What if I wanted to find critical values? Right? So let's say I had this alpha of 0.05. Instead of asking you for the p-value, I asked you for that critical value. Okay? So remember, the p-value is kind of representing a probability. The critical value represents a threshold cutoff for the number of standard deviations away from that assumed true difference. So for a right-tailed test, it's going to be the value that gives me that alpha of 0.05 in this right tail. And then the rejection region would be if my test statistic falls anywhere to the right of that critical value. So for a right-tailed test, I know my critical values will be what? Right? This distribution is centered around 0. If I'm on the right-hand side, positive critical values. If I had a left-tailed test, negative. If I had a two-tailed test, this is where we said there's alpha total in the tails. Right? So if this was a two-tailed test, I would have a pair of critical values that would be the same. One would be positive, one would be negative. Okay? But here we had a right-tailed test. So I'm going to look up and see what would give me 0.05 in that right tail. Once again, I'm going to cheat a little bit because I think it's easier to use that last row of the student T table, right? So go up here. I wanted 0.05 in that upper right tail. The standard normal distribution values of this last row. So 1.645, right? Now I think about, okay, where does my test statistic fall? The assumed true test statistic I was given was what? 1.67. So just barely in the rejection region, right? And those kind of decisions line up, right? We're just barely in the rejection region using that critical value approach. And we just barely rejected it using the p-value approach as well, right? We're just barely below 0.05. Our test statistic would be just barely above that critical value. Any questions over anything there? I mean, this is for you guys. It's like we're doing reviews, so I want to make sure if you have questions, you're getting them answered. All right. So we can come back to some of this Monday. So I think I'll skip around a bit. So I think we'll come back and kind of look at these mean difference ones on Monday. They're a little bit easier. Let's look at one where, we've looked at some of this different versions of this data set that was this GPA data set. So, wink, wink, I try to use data sets we've seen before to make it a little bit easier on the exam. So here, if I think about my dependent variable here was GPA, right? I've got all these other variables I've included on the right-hand side, SAT score, whether or not it's a student athlete, their high school rank, the number of credit hours they've taken, and whether or not they're female 1 or 0, right? So I've got, my coefficients. I've got my standard errors. I left kind of blanked out these test statistics, right? Because I might ask you to calculate one here. And then you have the associated p-values, like with all these variables. So what would be the correct interpretation on that coefficient for SAT? We've done this one a couple times, so hopefully we're kind of getting familiar with it. It's a 1 unit change in my X variable. So scoring 1 more point on my SAT would predict that GPAs or the predicted GPA from that would go up by 0.002, holding everything else in the regression constant, right? So holding everything else constant, every additional point on the SAT is correlated with a 0.002 increase in my Y variable GPA, okay? What if I wanted to interpret the athlete variable, or not athlete, high school rank variable? This one's kind of weird. How would I interpret that high school ranking variable, coefficient? So what would a 1 unit change in my high school rank be? Right? I can be ranked first in my high school. I can be ranked second, third, etc. So actually, this is a weird one because ranking, it's kind of like golf scores, right? Going up 1 unit in ranking is actually like getting worse, right? Falling down the ladder. It's just the way that we think about ranking. It's kind of a tricky one, right? So if ranking goes up by 1, that actually means, right, I'm just falling backwards in my class. So if my rank in high school goes up by 1, right, going from like 1 to 2, then the predicted change in GPA would be that it goes down by 0.003, right? Which makes sense. As I'm moving kind of down the ranking in my high school, it's likely that I won't do as well kind of at the next level. Okay? Now, I probably wouldn't ask you one that's quite that tricky on the exam, right? But I do want to kind of start to think about how to interpret all these coefficients. Okay? And then we've got some other ones that we could think about, like the kind of female variable here, right? So if I have a 1-0 variable, right? 1 if they're female, 0 if not, the interpretation, so the 1 unit increase is now going from the group that's 0 to the group that's 1. So a female student relative to a male, right? That 1 group relative to the 0 group, we would predict that that female student's GPA is about 0.18 points higher. I don't know where this data came from, so sorry to all the males in the room, but right, this would be the way that we interpret that coefficient. Okay. Problem 4 asks, how do you interpret the intercept? So this is where sometimes the interpretation of the intercept is weird, especially for these multiple, like when we have multiple X or right-hand side variables. Okay. So the interpretation for the intercept is always going to be, if I think about writing this out, I have like GPA as a function of all these things. So let's see if I can remember all of them. SAT score, whether or not they were an athlete, female coefficient, rank, and what's the one I left off? Guess I'll have to check. Rank, SAT, female, oh, total credit hours. So the way we interpret the intercept coefficient is if all these variables were equal to 0, well, then everything, anything multiplied by 0 is a 0. The only thing left with for our predicted GPA would be the intercept. So the way that we always interpret the intercept is if all the other X variables that we included were 0, the predicted value for Y, or the predicted value for GPA here, would be whatever that intercept coefficient is. So if someone with 0 SAT score isn't a student athlete, ranked 0 in their high school, which doesn't even make sense, right? But not female, and then 0 credit hours, their predicted GPA would be 0.8. So like I said, it won't make sense because we never actually see someone like that, right? But it is like, just, think about the idea of all of our data is kind of far away from the axis, right? But there still is some initial starting point for whatever this line of best fit is, okay? So that's how we would interpret the intercept. So for individual with 0 SAT, rank 0, blah, 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 the GPA would be whatever that intercept coefficient is, which is what, 0.803, okay? Any questions on that? So hopefully that should be, once again, another easy question, right? It's always just if all the X variables are equal to 0, the intercept coefficient is the predicted value for your Y variable, right? All right, another, what I think is easy, I think this should be the easiest question on the exam. It's kind of like when I said, I hope everybody gets the mean correct. If I ask you for a test statistic from some linear regression output, specifically here for the athlete variable, all I do to come up with these test statistics is take that coefficient estimate and divide it by the associated standard error. So when I'm looking at this, take that coefficient on athlete, 0.162, divide it by the standard error of what, 0.043. So all we have to do there is take 0.162 divided by 0.043. So this looks like it's gonna be approximately 4 something. So if I'm looking here, 3.742, I'm gonna go out on a limb and guess, oops, is what we end up getting for that test statistic, okay? And I'm just rounding, kind of eyeballing it there. That's how I said it's gonna be around 4, right? 0.04 goes into 0.16 about 4 times. And even just looking at like just goes in about 4 times, I could probably identify what the correct answer is gonna be here. Now, one thing, to point out is our standard errors here, in a way, what they really, like the standard error, another way to think about it, if it helps, is like, it's kind of like the standard deviation on that coefficient. So because it, in a way, represents a standard deviation, it's always positive. So the sign of your test statistic, right, if that standard error is always positive, is just going to be whatever the sign on your coefficient is as well. So because there was a positive sign on that coefficient, 0.162, we should know the test statistic needs to be positive as well. So we could rule D out right away, okay? But those test statistics for a coefficient are as easy as taking the coefficient, divide it by the associated standard error. So that one should be an easy one, right? Any questions on that though? I shouldn't say it's going to be easy. It's easy for me probably, but like that should be one of the easier problems on the exam in terms of like the computations are difficult. Yeah. Yeah. So if we want to interpret this SAT score variable, I'll just give you a general kind of interpretation of any coefficient, right? So a 1 unit increase in the X variable is correlated with a, whatever that coefficient is, change in our Y variable. And then we've got several X variables there. We also have to throw on holding all else constant over there on the right-hand side, okay? So for SAT, a 1 unit change would be like 1 more point on your SAT is correlated with, right, a 0.002 increase in GPA, if I'm remembering that coefficient correctly, holding all else constant, right? So when we're looking at those answers, you could say that holding all else constant first, but then every additional point on your SAT is going to be correlated with a 0.002 increase in GPA. But that's kind of the general form, right? It's a 1 unit change in the X variable is correlated with or would predict that the Y variable changes by whatever that value you see for that coefficient B or beta is. Yep. Any other questions? We keep moving here. All right, so the next set of questions, I've got kind of I probably would be a little bit friendlier on the exam than I was in this practice exam. But let's say you want to try to look at the relationship between median ACT scores and the previous year's athletic department expenses, right? So you've got that measured in $100,000, and you've got data on 97 universities, right? So I would probably, I kind of put this one up there. We didn't have as much time to go through some of the regression examples I wanted. So this one probably pushes you even a little bit further than I would on the exam. So this one has a kind of a weird units, right? It's not just dollars, it's $100,000 represents 1 unit. Okay. So what we're thinking about here is I'm trying to predict kind of the incoming ACT score of my freshman class using my previous athletic department expenses, right? So this was similar to the example that we went over, like with tournament success and leading to kind of seeing a higher quality incoming freshman class. However, this variable, the units, is measured in hundreds of thousands. So a 1 unit increase would actually be 100,000 additional dollars. Right? We're told that when we're trying to come up with these predictions, I don't think I gave you the intercept, but I believe I told you the coefficient on that athletic expense variable was 0.3. Right? So if we think about interpreting that coefficient of 0.3, right, it's going to be a 1 unit change in my X variable, which here 1 unit is $100,000. So if I spend an increase of $100,000, right, on my athletic department, that's going to lead to a predicted change in my ACT of ACT goes up by that 0.3 slope coefficient. Okay. So here it was a little weird where I had my units was hundreds of thousands of dollars. I probably wouldn't push it that far in the exam. I would give you something where it's like, you know, measured in inches, dollars, years, right? The unit is just kind of our more, you know, smallest unit of measure there, as opposed to you could have it where the data comes in and for, you know, $500,000 of spending, all you see is 5, right? And that's representing hundreds of thousands of dollars. And that's pretty common when we're looking at, you know, dollar amounts that are very high. So a 1 unit increase going from 5 to 6 would actually represent going from 500,000 to $600,000. So an additional $100,000 spent on the program, because that's 1 unit here, would lead to the incoming freshman class's ACT going up by 0.3. Okay. So if we're trying to identify a $100,000 increase in men's basketball expenses correlated with a 0.3 point increase in the median ACT, that would be the answer here. Okay. Any questions on that one before we keep moving? All right, let me see what I've got here. I got 10 minutes, so I want to make sure I go through some stuff. So one thing to kind of, I don't know if I'd ask necessarily a question this exactly like this on the exam, but it's a good thing to know. When we're looking at these coefficients, we had just talked about calculating standard errors. The table gives us p-values. The type of test that we're always going to have for these coefficients, we said the null hypothesis is always that these slope coefficients are equal to 0. And I said earlier, that's always coming from a student t-distribution. So we're always going to have a two-tailed test, and we're always going to be using that student t-distribution when it comes to these coefficients. Now, I don't make you go through the practice of finding the p-values. That's a little bit more kind of complicated than what I want you guys to do. But this will always be the type of test that we would use. I also could ask you, well, which of the variables that were included in that regression have a significant relationship with GPA? Right? Well, so that's going back to that previous example for a second, because I do want to go over this real quick. We only reject this null hypothesis, the same sort of thing as when we're looking at the difference in means or the difference in proportions. We only reject that null hypothesis if our p-value is less than alpha. So we start out assuming there's no relationship between any of those X variables and our Y variable GPA. If we get a p-value that's low enough, we reject that null and instead say that variable has a significant relationship with our Y variable or GPA in this case. So if I go back up here, which of these variables can I say have a significant relationship would be the ones which I could reject the null. Well, if I look, these e to the negatives, remember, these are basically p-values of 0. So every variable I included here has a p-value of 0, so I could actually say all of them are significant. Now, I don't know if I'll be as friendly on the exam as that. I might have something where it's like, you've got p-values that are kind of in different ranges. Here, all the p-values were 0, so it didn't even matter what level of confidence I wanted to be able to reject the null with, right? It was going to be less than any alpha. But on the exam, I'd probably give you, at the 10%, 5 or 1% significance levels, maybe I give you one of those. Which variables can you say have a significant relationship? And you have to remember the ones that you can say have a significant relationship are the ones for which you could reject the null, that have a p-value that's lower than alpha. Because we start out assuming no relationship, so if we can reject that null, we're saying there is a significant relationship between those two variables. Okay? Any questions on that? I'm kind of jumping around a little bit here. One thing I might also do, so this one, there's the last question on here, just so we go over it, is kind of this idea of, maybe I find a certain coefficient and, even if it has a very low p-value, so in this case, spending on the basketball program and ACTs, I say, well, geez, if that's increasing the ACT score, we should just start dumping all our money into our athletic programs. Well, this is where we have to be careful, where these aren't causal relationships, they're just evidence of a correlation. So especially when we run something that's naive, where we don't include any control variables here, right? We're not holding anything else constant. We might be getting a bias estimate, right? And so it could be some outside omitted variable that's actually causing both of these to change, right? So we want to be careful and not interpret these as causal relationships, but remember that they're just evidence of a correlation, which if I give you a question like that, right, what's wrong with the logic? It's just evidence of a correlation. So it only provides evidence of a correlation. There's likely some omitted variables here. We ran a pretty naive regression. Okay. Any questions on that before I keep moving here? Yeah, one more thing I think is really valuable to kind of show you that's related to this example. So let's say we had this setup where we had this ACT of the freshman class and we're predicting it with basketball expenses, right? So let's say I give you that coefficient of 0.3. Let me just think what makes sense here. And let's say I tell you the intercept coefficient is 25. So maybe I do something like this. I give you, the regression equation. Previous, what was it, athletic expenses. And then I tell you, assume you found that A was equal to 25 and B was equal to 0.3. Right? So a question I could ask if I gave you the values of those coefficients is, what is the predicted ACT of the incoming freshman class? I'm not going to write all that out. For a school spending, we'll kind of make this one a little bit tough, $1 million. Right? Well, here, this is kind of a weird one where we said the units of this basketball expenses were in hundreds of thousands. So I said, if I was spending $500,000, that would actually look like a value of 5. Right? So $1 million, the value for my previous athletic expenses would be what? Yeah, there's 10 100,000s in there. So to come up with this prediction for ACT of my freshman class, I would take that intercept value of 25. I would then add to that the coefficient on my X variable times the value of this hypothetical university, right? So I get what? 10 times 0.3 here is 3. So I get my predicted ACT would be 28 for this university, right? So I might do something like that where I give you these hypothetical values for your X variable. I give you the values of the coefficient. You should be able to come up with those predictions. That's what we're really trying to do, right? These coefficients are allowing us to come up with predicted values for Y. Now, it could be more complicated than just one variable, right? I could do something here. I probably wouldn't with like as many just for the sake of time. But right, you could come up with a predicted GPA if I gave you some hypothetical values for a person here, like maybe they have a 1300 SAT, they aren't a student athlete, they're 40th in their high school, they're female, and they've 30 credit hours, right? I would just take those hypothetical X values. Instead of zeros here, when we were doing the interpretation of the intercept, I would just write those in. I think I said that they weren't an athlete, they were female, 30 credit hours, 40th in their high school. I then have values for the coefficients. Now I've just kind of got this long kind of linear equation where I just have to kind of go through it and do the math there, right? So I would take those coefficients, multiply them by the X value for this hypothetical person, add them all up, but make sure I don't forget the intercept as well, okay? Any questions on that? So sorry, I opened up the wrong practice exam to start out, but actually we might return to that. Maybe I'll save that and make it practice exam C. So we have a few more questions because I think some of those will be good to cover starting in class on Monday. So Monday, we'll just keep doing review. If you get a chance to look through some of those practice exams, watch those videos on practice exam A. That might be some good review. And if you have questions that you can bring Monday, I'll start with those. Otherwise, we worked through most of practice exam B. We only had a couple questions left. So I do those and then probably look at this other practice exam C that I'll kind of put up there as well. Okay. Yeah. No, Monday is the last day of classes and then it's kind of exam week. I don't know why they have that. I think it's something about the number of hours we meet for Monday. They need to, make it total. So we'll just be doing review Monday and then we'll talk more about the number of questions on the exam and things like that then as well.
What is the title